Geometric approach and technique for solving integer problems.
Okay, so thank you for coming to my class, and have you read my abstract? Yes. Okay, who have solved the first problem that I have written in the abstract? No one? Okay, that's good. Then you will be learning something from my presentation. Let's do this one. Let's do the easier problem. Sum of two squares that will add up to 25. Okay, who have solved? Who knows the answer? Okay, I see the hand. Present.
5. Or there's one way to do it. 5 squared plus 5 squared.
Okay, another way is?
Oh, there's another way? Yeah, 3 squared.
9 and 4. 3 squared plus 4 squared.
I hear a bunch of answers, okay. Yeah, I heard like 3 squared plus 4 squared, and that reminds me of Pythagorean theorem. Yay! And we already know this one, right? So, when we have the c squared to be 25, or c to be a square root of 25, then I can express it as a sum of two squares, 3 squared plus 4 squares. Or if I draw it in a Cartesian plane, which the 25 is the radius of a circle, square root of 25. So I'm going to draw a circle, and all the lattice points that is passing through the circumference will be my solution set. And removing the redundancy, the symmetry, the answer for the easy part is 0, 5 or 3, 4. Is that clear?
Yes.
Okay, so I want to introduce something. It's pronounced galvagosmetic. That's a tongue twister, but I have a friend. Her name is Liu, and she didn't do well in the conventional math. She had struggled understanding the math, so she had to invent math by herself. And her approach was very much geometric. And I like that approach. She was talking in her own language, so it took a time for me to understand what she was talking about, but once I understand, it's a great thing. So this is how she does. 0 is an origin, and 1 is a basis. Two important numbers, and two important fundamental operations, which is, of course, addition and multiplication. Addition is fixed basis and moving origin. Multiplication is fixed origin and moving basis. Can you see the symmetry between those two? Okay, it's not clear. It's not easy to understand if I just say it in the words. So let me demonstrate it. 3 times 2. So this is a pretty easy multiplication, and I'm going to do it in a number line. First step is to identify which one is a multiplicand and which one is a multiplier. If you want to identify it other way around, that's totally fine. I'm not forcing the order. But let me do it this way, because I'm more used to this one. Then, after you identify, you copy the number line, you fix the 0, and you stretch it. You stretch it up to the point that the new number line's 1 matches the old number line's multiplicand. Then when you look at the new number line's multiplier, then that will be your answer, which is 6. This works not only in just a number line, but anything. So for example, in complex numbers, this is 2-dimensional. Let's do 2 plus I squared. So which is the same as 2 plus I times 2 plus I. And I have one multiplier and multiplicand. So I'm picking a multiplicand and I'm setting new coordinates, 1 to be the old coordinates multiplicand. Then, when I look at the new coordinates multiplier, that's pointing out to be the answer, 3 plus 4i. And I want you to pay attention that the length for that multiplicand in the old coordinate is square root of 5. And also the length for the multiplier in the new coordinate is square root of 5. And when I multiply square root of 5 times square root of 5, that will of course give me square root of 25, right? In the new coordinate system. So that's the representation of the easier problem. How I can present it. How I can generate 3 plus 4i systematically. I can factor out 25 into 5 times 5, and just by multiplying, I can generate a sum of squares. Okay, so this is 2 dimension. I have used complex numbers because it was a sum of 2 squares. The original problem was sum of 4 squares, so I'll be needing 4 dimension. Obvious? No, not so obvious. Okay, so I'll be introducing quaternions. We will have 3 imaginary numbers, I, j, k. This is an extension of complex numbers. We are familiar with the quaternions with like contrast between dot product times cross product, or 3-dimensional rotation modeling, like in computer science. And I've also learned this in electromagnetism in physics. And there are many more applications, but I don't have a space for them. Here are some important identities for quaternions. And these are not so obvious, but I will explain them later. In order to explain, I need to show you the 4-dimension. Does this look like a 4-dimension? Not really. It looks like 2-dimension. This is a 4-dimensional hyperspace being projected into the 2-dimensional plane. And in order to understand this, I'm picking 2 axes. Let's say I'm picking the 1 and I. They're perpendicular and they will make a plane. The remaining 2 axes, let's say j and k, are also perpendicular and they have a plane. So 1i plane and jk plane are also perpendicular to each other. And it doesn't have to be this way. You can pick any 2. So I can also pick 1j plane to be a perpendicular one to ik plane. Or I can also do 1k plane being perpendicular to ij plane. So let's see how this one works. I'll do I times j equals k. The same thing. So first, I'll copy the coordinate system. And next step, I will set the new coordinates 1 to be the old coordinates multiplicand, so I'm going to rotate like this. So now I have the new coordinates 1 matching the old coordinates multiplicand, which is I. And when I look at the new coordinates j, that will give me the answer k. And if I change the order, j times I, I'll repeat the same process. I'll copy the coordinates and I will rotate so the new coordinates 1 will match the old coordinates multiplicand. And if you're wondering why it rotates like this, it's hard to explain, but because if you don't see the 4-dimension, it's hard to explain. But once you change the position of one point in a space, you'll be changing the position of entire thing, except the origin 0. So everything will be moving. So 1 in the new coordinate matches the multiplicand j, and the I in the new coordinate will match the answer, negative k. So let's go back to the main problem. Sum of 4 squares is equal to 130. So now I'm having some distance from the point of origin. The distance is square root of 130, and we'll be doing the prime factorization. Who can do it?
2 times 5 times 13.
Yep. 13 times 5 times 2. Okay, I did it in the other overview, but that doesn't matter. So let's try to express what's 13. It can be expressed like 3 plus 2i, because 3 squared plus 2 squared is 13. Or I can do 2 plus 2i plus 2j plus k, because 2 squared plus 2 squared plus 2 squared plus 1 squared is 13. This is not the only way. You can also do other ways, but they will be symmetric. Let's do 5. I can express it like 2 plus I, or 1 plus 2I. 2 squared plus 1 squared, or 1 squared plus 2 squared. Both of them will be 5. And square root of 2, I can do 1 plus I, or 1 plus j, or 1 plus k. So when I multiply them, I'm just multiplying 12 times, right? 2 times 2 times 3 will give me 12 times, and I can generate all the answers. Isn't it nice? So let's do it. This is all the 13s. It looks a lot, but not really. I'm just repeating. And these are all the 5s, and these are all the 2s. I'm removing the ones that will generate a repetition, redundancy. And let's see the answer. Here's the answer. I'm skipping how it works, so if you think my work is wrong, please check my work. And once you generate it, you can translate all of these answers as a sum of squares. And all of them will add up to 130. It's a very systematic way to generate, right? So the final answer for the main problem is these ones. I just arranged it in a nice order, but that's it. So there are only 10 ways. And finally, homework. This homework is not graded, so you don't have to do it, but it's a very beautiful problem, so take it home. Try to express 13 raised to 8 as a sum of 2 squares. You can already do it. I've already taught you how to do it. So any questions? Yes?
Can you go back and explain the quaternion multiplication, like how it rotates?
Okay. This part? Yeah. How it rotates, yeah, it wasn't obvious.
Both planes are rotating, right?
Yeah, both planes are rotating. So when you pay attention, this one, you look like, it looks like the plane is rotating otherwise, but it's not necessarily always otherwise. What's important is when you multiply and when you rotate, how do I say it? I mean, I can see the 4 dimension, but I can present it here. Yeah, so the new one is matching the old I. So you have to rotate 90 degrees for the orange one. But the green one will rotate in other direction so that the green one will follow the pattern for I times j. I mean, if I go back to the previous slide, for this one, I've explained that there are many ways to see the 4-dimensional space. I can pick 1 and I as one plane and j and k as another plane in the next slide. But you don't have to pick that way. You can also pick other way around and you will still end up with the same answer. Any other questions?
All right, let's thank our speaker one more time.